concepts in math. So this is back to R1. And I just want you to see how our numbers, when I say integers, when I say rationals, when I say those words, I want you to know what they mean. So just going to scoot down really quick. You may recognize set builder notation in here, but I really am after this little table right here. So we have the way that they're doing the lists here, the way they're showing sets is they're just starting up a pattern and then putting an ellipsis on each end. You have your natural numbers, and they're called that because they're also called counting numbers, right? 1, 2, 3, that's what we would use. Whole numbers is the set that contains all the natural numbers plus 0. Okay, believe it or not, 0 is a relatively recent discovery invention. And the reason for it is that there's no reason for you to write down all the things you have 0 of, right? 0 is not, I don't need to tell you that I don't own any roller coasters, right? But if I go down the list of things I don't own, that's going to take forever. So 0 is relatively recent, and it's a big deal for placeholders for the way that we represent numbers in our base 10 system, but it also works for all the bases. Next, we have the integers. The integers are all the natural numbers, all the plus 0, which is all the whole numbers, and all the natural numbers negative counterpart, right? So I've got 1 has -1, 2 has -2, 3 has -3, and so on and so forth. So this goes on forever. Here's the thing. All 3 of these sets are infinite. Okay, the size of the sets are infinite. So that means my natural numbers is infinite. My whole numbers is infinite. Even though it's got more elements, it's still infinite. And this has what? This has twice as many as the natural numbers, right? And it's still just infinite. So we'll get into infinity at a later time. But here's the harder parts of it is the rational numbers. And the set builder notation, I'm just going to walk you through it. Got my curly brace, and it says P over Q. So the first part of my set builder notation gives me my form. Then that bar, this little straight up and down bar, reads such that. How does this read? P and Q are, this is elements of Z. Z, or the set Z is the set of integers. You can see their little shorthands here. You have an N with a double bar for natural numbers, a W with a double bar for the whole numbers, and a Z with a double bar for the integers. So the rational numbers are Q with a double bar. And this says the rational numbers consist of all numbers that can be written in the form P over Q, where P and Q are integers, meaning they can't be fractions or decimals. And Q is not 0. Q can't be 0 because division by 0 doesn't make any sense. It's inconclusive. We don't know what it would do. We don't know what it means. So rational numbers can be expressed as a ratio or a terminating or repeating decimal number. So 0.666 repeating, that's 2/3. It goes on forever. It continues popping up sixes. That is a rational number. What's not a rational number? Pi, the square root of 2, the square root of any prime number. Anything that cannot be represented by either a fraction or a repeating or terminating decimal. Okay, the irrational numbers are here. I have never seen this before as a double barred H, but I'll take it. This will allow us to write all those numbers, pi, e, roots of prime numbers, and so on and so forth. Now, how does this work? Well, it builds up, right? The natural numbers are completely contained in the whole numbers. The whole numbers are completely contained in the integers. The integers are completely contained in the rational numbers because all integers can be rewritten as -3/1, -2/1, -1/1. All of those integers are contained in this rational set, But then when we get to the rational and the irrational, this is where they're not building anymore. The rationals are here, the irrationals are beside it, but they don't overlap. So when I want to draw it, it looks like this. So natural numbers, whole numbers contain all the naturals, integers contain all the wholes, rationals contain all of the integers, irrational numbers are here to the side, and when you put the rationals and the irrationals together, you get the real numbers. And the real numbers are represented by a double-barred R. All right, so if you ever see, I always thought it was cool in school to learn these really neat things so you can make it look like you're doing really difficult math when in fact we're just trying to make things easier, right? Let's see if anybody, for 5 nerd points or cool points, does anybody know natural numbers start with an N, whole numbers start with a W? That makes sense. Why would this be a Q? Any guesses? Does anyone know it? Why would the rationals be represented by a double-barred Q? No? Okay. So take a look at all the forms here. Yep, exactly, Emma. Nailed it. Q for quotient. And then Z for integers. We don't want to use I here because I is for imaginary. You're going to have to speak German to get this one. So this is a remnant of the German. So that's why our Z starts that's our representation of the set of integers. Okay, so I wanted to get those down. The only thing missing from this is the complex numbers. So they're the real numbers. There's that double-barred R I talked about. All of these together, the rationals and the irrationals together, make the real. The only thing that's not in the real numbers, for as far as we're concerned, is the complex. Complex is when we start putting in i's, where we have the square root of -1. Excuse me. Oh, all right. So I wanted to talk through that. And now I want to jump over to the notes. Okay. So like I said, you're going to notice the format's different, but I think my writing is going to be better enough. No, you don't need to write that down. You'll always have access to that in the text. And you can always refer to it, that all those sets and stuff, that's all over the internet. But I did want you to know, so when I start talking about where W is an integer or W is a natural number or W is rational, I just want to make sure that we understand what we mean by that. So it's not going to be, you won't be tested on it, but it's going to be, instead of being tested on it, it's going to be expected vocabulary at this point. All right. We won't see that for a little while at least. So I'm asked, we did 3 of the problems in R3 before class ended. And then we didn't get to the 4th. Now, this was just page 2 of the notes. Let's see here. So this last one, it says expand. What is that going to look like? Well, first off, let's make expand large so that everyone can read it and not just tiny ants. It's not going to let me. Okay. So anyway, well, expand this. And what is this? This is quantity, W to the N minus Y to the M, closed quantity squared. All right. So what does that mean? That means W to the N minus Y to the M times W to the N Y minus Y to the M. All right. Now, follow our rules. First, W raised to the N times W raised to the N is going to give me W to the N times W to the N. And outer w to the n times negative y to the m is going to be minus, I'm going to absorb the minus right here, w to the n times y to the m, inner, same thing, y to the m times w to the n, and then last. And this is a negative y to the m times negative y to the m. So this is going to end up being plus. If you want to write it all the way out, what's happening there is you could write them all out as pluses and then do your double negative like this, just in case you're trying to figure out how that happened. All right, so what have I got? Same base. What do I do to the powers? I add them. So w to the n times w to the n is w to the 2n, which is n plus n. Okay. Minus w to the n times y to the m. Nothing to do there. But I'm minusing the same thing, right? Multiplication is commutative. So w to the n times y to the m times w to the n. Those are like terms. So there are two of those. This is subtraction. So we're just combining terms. And we really don't need the parentheses anymore. And then lastly, negative y to the m times negative y to the m. Negative times a negative is a positive. Y to the m times y to the m is y to the 2m. And there it is. Questions on that? Any problems? Any issues? Okay. Now the next page just has some problems listed for you. I'm not going to go into them because I want to move on. But if any of this sounds like material that you need to look at or need some review on, this is a great place to do it. We have nth roots. We have fractional exponents, adding and subtracting polynomials and multiplying polynomials. Okay. If I was going to do anything, you are probably confident with this, adding and subtracting polynomials and multiplying them. If I was going to review anything, I would take a look at these two, fractional powers and nth roots. We already talked about nth roots on the very first page. Okay. So let's talk about factoring. Now, factoring does not, it has different processes depending on the problem that we're looking at. I can factor some number out of a larger number, or I could have a polynomial in front of me. I could be asked to factor that, in which case I can factor out a greatest common factor. I may even be able to reverse FOIL and break down a trinomial into the product of two binomials. Who knows? So when I'm going to factor, here are the questions that I ask myself. Is there a GCF? So if I'm plus 6x minus 3, do I have a GCF in here? Do I have a, and let me be clear with the language here. Is there a GCF? Yes, there's always a GCF. It's just sometimes it's 1, which means nothing happens. In this one, that's not the case. X doesn't exist in all the terms, so that can't be my greatest common factor. But 2, 6, and 3 are all what? Or do I have one? Is there a number or variable that you see is a factor of all 3 terms? No, so that GCF is 1. What about this. 2y squared minus 4y minus xy. Yep, I got the y in here. So when I say factor out the GCF, it means pull the y out. What does that do? What's the actual operation that's taking place here? When I factor out a y, in order to find out what am I left with, I divide each term by y. Yeah, exactly. So 2y squared divided by y is 2y. Minus 4y divided by y is minus 4. Minus x times y divided by y, x. Ooh, that is sloppy. Let's clean that up, Larry. This is college, man. Come on. All right, 2y minus 4 minus x. Okay. Now, the next question, does the polynomial fit a pattern? Okay, what am I talking about? Well, I'm talking about cases of difference of perfect squares, sum of cubes, the difference of cubes, or a perfect trinomial. All right, so if you run into any of these forms, what that's going to do is make factoring super, super easy for you. Okay, the others are, if you see it in these forms, the perfect a plus b squared looks like a squared plus 2ab plus b squared. A squared minus b squared already has a form. I'm going to put that one back in just a minute. That's a squared minus 2ab plus b squared. So that's 1. That's 2. You may see this, and then you may also see the difference of cubes. Okay? So if you see a polynomial that's in this form already, then factoring it can be super easy. All right, so there we go. Terms can be the difference of the sum of squares or cubes. That's this and this. Let's see. It's going to let me pull. There we go. No, that's a bad idea. All right, so there. But you get the idea. I could be looking at the difference of cubes. I could be looking at a perfect square trinomial. Oh, I'm sorry, Emma, what's up? Here, let me fix that. All right. So if I give you, here the question is saying, if I give you a polynomial, how do you factor it? Yes, I'm trying to, okay, Stephen, no, this is good. This is good. What I'm trying to do is factor the equations. So, like this, for instance, x squared minus 2x plus 2x minus 1 minus 2x plus 1. So if I give you this and I ask you to factor it, what I want to do is I want you to get, if there are two things that multiply to give me this, I'd like to break it down into those factors. If I had 7a plus 14, and I say factor this or simplify this, that means pull out all the common factors and rewrite this as multiplication, right? I want to see what are the factors. So when I say to factor something, when I get done with this, I'm going to end up with factors. For this polynomial, or this trinomial here, this one follows a pattern of, this is a perfect square. this is a perfect trinomial. This is the two numbers that multiply to +1 but add to -2. Those are -1 and -1. So this is x minus 1 squared. That's the factored form of this trinomial. What variables or numbers make up the equation? Whichever ones they want to be. It doesn't matter as long as the numbers fit into the pattern. So let me write out these patterns a little better this time. The difference of squares would be, how have I got that written down? A squared. If you have an equation that looks like, and the A and the B are going to get a little confusing. Difference of squares. If your formula looks like a squared minus 2ab plus b squared, that is the difference of, that's the a minus b all squared. If you look like this, plus 2ab plus b squared, this always factors into this form. If you have a squared minus b squared, that's the difference of squares, and that always factors down into a plus b times a minus b. So if you get a polynomial that fits one of these patterns, you can factor it. Take a look at our polynomial. Look at this guy. This matched up with one of those patterns, right? Isn't that the same as this? Right? I've got a squared minus 2ab plus b squared. Now, in these forms, a can represent just a single number. It can be a number and a variable together. But what it is it's got to be squared. So does it represent with, this looks like something squared, a squared, so I'm going to let a be x, minus 2 times a times b. Okay, well, if a is x and b is 1, because b squared is 1, that means b is 1, then I have this perfect form. Now, if you don't see that perfect form, but you can factor this because you know two numbers multiply to 1, add the -2, that's fine. That's preferred, honestly, because then it's not as confusing. You don't have to remember all these forms. Okay, but these exist. You will always have access. You'll always be able to make a note to use 1 page of notebook paper. So, for instance, I don't know the difference of cubes equations or forms that I don't know them that well. So we could be looking at a cubed, excuse me. If you had the difference of cubes, this would always break down into a minus b times a squared plus 2ab plus b squared. I don't know that one off the top of my head. So if I'm ever going to use it, I've got to have access to that equation. So whenever it comes for sometimes for a test, you would definitely want to write some of these down just in case you encounter them later on. All right. So let's move on to the cases of, are there 3 terms or are there 4 terms or are there 2 terms? If there's 2 terms, this is typically a difference of squares, difference of perfect squares, a difference of cubes, or a sum of cubes. If there's only 2, there's only a first term and only 2 terms in there, this is usually going to be one of those cases. Okay. If it's 3 terms, it's probably going to be a reverse FOIL situation, or the cross method, which people have talked about, and I've just never seen it work. So I have brought in bottoms up, which is something that I learned a couple of years ago that I think is useful. So if there are 3 terms in here, the things we're going to attack with are reverse FOIL and the bottoms up method. If you know the X method or the cross method and you want to use that and it works, great. The last one here is, are there 4 terms? We're going to factor by grouping if that's the case. Now, I'm going to show you some examples. So don't think I'm bailing on you by not writing anything there. Okay, first thing we have is the factored form of the difference of squares. So a squared minus b squared factors into a plus b times a minus b. So come down here and take a look at our examples. I don't know. How does that look to y'all? You probably want this expanded. All right. So whenever I have a polynomial that I think matches up one of the forms that I know, what I need to do is figure out if these match up. So for example, question A, I got t squared minus 121. All right. I say this is the difference of squares because t squared is a perfect square and 121 is a perfect square. What are those perfect squares? Well, square root of t squared is t, right? So I'm saying that this looks like t squared minus 121 is the square of 11. Okay. And once I know that, now I just need to follow the pattern. The rule says if I have the difference of perfect squares, that this will always factor into a plus b times a minus b. Well, what is a for us? It's t. What's b? It's 11. A plus 11 times a minus 11. A gets swapped out for a t. Okay. So for this section, the key is I need to figure out the a and b that make this statement, this algebraic statement, match the pattern that I've seen above. Now, the next one, okay, what do I have? Okay, well, this one's not as easy because anytime you're doing factoring, the first thing you need to do is make sure there are no common factors in the terms. In this one, we do have a common factor of z, right? There's a z in the first term, there's a z in the second term. So I'm going to factor out that z, and that's going to leave me 625 z to the fourth minus, factor out the z, which is dividing, z divided by z leaves me a 1. Don't forget that 1. If you forget that 1, you've changed the problem completely. Now, do I have the difference of perfect squares? Maybe. Possibly. Thoughts? Okay. Yes. Okay. What are the squares? So what I'm saying is this looks like a squared minus b squared. Square of 1 is 1, good. So for us, b is equal to 1. What is a? Well, I have z to the fourth here. I'm going to help break this down. 625 is 5 to the fourth. All right. So that means I could come back and rewrite this as 5z to the fourth. Now, what do I need that power to be to match up? I need that to be a square. How can I make this a square? How can I take something raised to the fourth power and make it a square? Square root? Ooh, if I take the square root of what I have right now, what happens? I would end up with just a 2 up here, right? So what I have is a power raised to a power. So whenever I have the power raised to a power, have this is squared. If I square the square, don't my powers multiply? 5, oh, I got an X in here. What am I doing? 5z squared all squared. Doesn't that give me 5z to the 4th? And now I have something squared. What is it? So 5z squared is 25z squared. Now I have found it, that a is 25z squared. So if this is the case, if a is 25z squared and b is 1, and I have the difference of perfect squares, what does this thing break down to? 25z squared plus 1 times 25z squared minus 1. Okay, and then out front, I still have that z. So it's got a little sloppy over here. What I said is 25z squared minus 1 breaks down or factors into these two factors. Okay. So just off to the side, I get this. So that means my final answer for this question is what? Well, there's a z out front. I have 25z squared plus 1 times 25z squared minus 1. Okay. Now this middle factor won't go any farther, but the last one does. This is the difference of squares. So this would actually factor again. 25z squared plus 1 times 5z plus 1. Oops, that's not a parenthesis. That's 5z minus 1. All right, raise your hand if you're confused. Good. Anybody else? Okay, good, good. I like the honesty. I like it. All right, so where do you want me to go back to? Where could I go back to and help make this make sense? Let's start back up here. See if we can break it down again. Okay. It's good that we knock this out. Get all the bugs out. Yeah, I think you're right too. I think that's the amount of steps and the amount of things we did in there just naturally lead to confusion. Okay, it's the foundation of the problem, and that too. Okay, so let's start back here. And first step, so if I'm going to reduce or factor something, remember factor can mean a bunch of different things. Factor can mean pull a common factor out of a polynomial, binomial, trinomial, polynomial, whatever, or it can mean break a specific binomial or trinomial into its factored form. right? 4x minus 8, that means pull out the 4 and leave it in its factored form. This is the factored form because factored form means I have factors instead of terms, right? So for this, right now, this is written in terms of x, right? 4x minus 8. When I say give me that in factored form, look at what changed. 4 is a factor, x minus 2 is a factor. Okay, x squared minus 2x plus 1. This is a trinomial. There are no factors that are common in all three terms, but we know this breaks down into its factored form, x minus 1 times x minus 1. Okay, both of these problems could say factor. They both mean to factor. Okay, but you can see where it looks like it's two different things when in fact, when I say to factor something, what I mean is it's currently written in a form that has some terms in it. I'd like it written in factors. So this is in factored form now. This is in factored form now. Yes, you can simplify, or yes, you can combine those to the square term, but that's really not the point here. It's getting it from its polynomial form to its factored form. So over here, whenever I'm asked to factor, good. So whenever I'm asked to factor, my first step is always to try to make any common factor come out front. And in this case, I had the z. So both terms have a z. It doesn't take a whole lot away, but it does take away one z from this x to the z to the fifth, so that leaves me a z to the fourth. And it factors out a z from this term. Factoring a z out is done by using division. Z divided by z leaves me -1, or leaves me 1, and that minus is there. Okay? Now, am I done? No, because this is, I have a binomial. Even though this is to the fourth power, this is still a binomial, because remember that those only concern themselves with how many terms are there. This is a binomial because there's two terms. I got two terms and they're subtracted. This could be the difference of squares or cubes. Well, this is to the fourth, so it's probably not cubes. Maybe it is a difference of squares. So let's break this down. And what is 625? 625 is 5 times 5 is 25, times 5 is 125, times 5 is 625. So that breaks down into 5 to the fourth. Okay, so I got 5 to the fourth times z to the fourth minus 1. And then there were two, here are the two steps where I assumed confusion would reign supreme. I have two things to the fourth, so I can just rewrite them as to the fourth, factors raised to the fourth. And then I said I want to make this look like a squared minus b squared, right? I want this to look like the difference of perfect squares, okay? Well, I can do that because z to the fourth is the same thing as z squared squared, and 5 to the fourth is the same thing as 5 squared squared. So what I get is 5z squared squared minus 1. All right, so the thing that is squared, because remember the goal of this is to look like this, we want to look like this. Well, if I'm going to look like that, A must be 5z squared, and B must be 1. So The reason I know this, or the reason that I wanted it in this form, is I know that the difference of squares always looks like this. A plus b breaks down to a plus b times a minus b. So fill it in. If a is 5z all squared, b is 1, and I just said it out loud and wrote b anyway. Sorry about that. A is 5z squared. B is 1. A is 5z squared. B is 1. Now, square these 5z's. That's going to give you 25z squared plus 1 times 25z squared minus 1. So all of that work to come back and say that this is z times 25z squared plus 1 times 25z squared minus 1. And then the last step is the real kick in the pants of, oh, and by the way, this is the difference of squares, just like this was the difference of squares. So this follows the same pattern. If this is the difference of squares, then that factor breaks down again into what? Well, A is 5z, so this is going to break down into 5z plus 1 times 5z minus 1. And there's my answer. It doesn't work for the plus in the middle because there's no special situation of the sum of squares. It only works for the difference of squares. All right. Better, maybe not perfect, but better. Okay. How do we know if it can be factored further when we fully factor it? If every factor doesn't have a factor in common, which we took care of that very early on, and nothing left reduces by any of those forms that we saw: difference of squares, difference of cubes, perfect square trinomial, or a common factor in each. Once all of those have been met, then we know we're done. And order doesn't matter. Order doesn't matter, but z by itself is called a monomial because it's just one term, or one. So it's a single term, doesn't have any pluses or minuses in it. And anytime you have a monomial, it's always best to put that first, because putting this in the middle between two binomials is going to get really confusing. So if you ever factor out a monomial, factor something out, always leave that at the beginning just to save yourself some confusion later on. All right. Now, I'm going to do the top one over here on 10, and then I'm going to move on. U cubed plus 27, and then we'll post those notes so everybody can see them. U cubed plus 27. Now, this one I did not know right off the top of my head. Again, because I have never dealt with the sums and differences of perfect cubes. So the rule says, let me find it. If I have, where am I? Here we go. If I have a cubed plus b cubed, this will factor into a plus b times a squared minus ab plus b squared. Okay, this is called the sum of cubes. Okay, so do I have that situation? Is my first term something to the third power? Yes, u is to the third power. Is my last term something to the third power? Yes, because 27 is 3 cubed. So follow our pattern here. We're saying a is equal to u, b is equal to 3. By the rule, this must factor into a is u, b is 3, a is u, a is u, b is 3. So all I did is just plug in u for a, 3 for b, and then I'm going to come back and clean it up. U plus 3 times u squared. U times 3 is the same thing as 3 times u, and then 3 squared is 9. All right, so there is a perfect sum of cubes situation. So again, you'll know you're done when this doesn't factor, and you can look at it. If this ever did factor, or if this always factored, then the original formula would be broken down more. This is not going to factor, at least in this situation. Two numbers multiply to positive 9 and add to negative 3. That one's not going to go. All right. So there is sum of cubes, and yeah, there's a sum of cubes. Oh, I see. You're missing a box right here. That's why. If b wasn't 1, that wouldn't be factorable. You're absolutely right. In the second one, yeah, if b wasn't 1, it would have to be something to the fourth. So it would have to be 16 or 81 or 1, because that one goes all the way out to the fourth power. You're exactly right. Now, I just noticed what's missing. And what's missing is the sum and difference of cubes. You have it in the printed out notes, but I did not put it in these. There's a little picture. It's going to go right there. So it's going to make these problems a whole lot easier to deal with. But yeah, I just don't have that in there right now. So let's deal with factor by grouping. Factor by grouping is for the cases where you have 4 terms. And what you do is you just isolate 2 terms together. The middle grouping does something a little funny, so we're going to do that one last. But what I mean by factor by grouping is I mean group the first 2 together, and then this is something that I do. The book doesn't do this. If it's a minus sign in front of that third term, I always rewrite that as plus negative. And the reason for that is when I need to factor something out, it makes life a lot easier. Okay, so what I have are 2ax minus 6ay plus negative 5x plus 15y. Next step, I'm going to pull out any common factors in the terms that I have grouped. So these first two, 2ax and 6ay, they both have a 2 in them, and they both have an a in them. So if I factor out 2a, what's left is x, and then negative 6 divided by 2 leaves me negative 3. The a divided away, the y is still there. Okay, and now this is plus 5x minus negative 5x plus 15y. I'm going to pull out that 5. That's going to leave me negative x plus 3y. Now, if we do this right, the two binomial terms that we end up, binomial factors we end up with, are going to be identical. They almost are. It's just the signs are flipped, right? This one has a positive x and a negative 3y. This one has a negative x and a positive 3y. I can't pull it out yet. I need to make these match up perfectly. So what I'm going to do is take out a little bit more by taking out a negative 5 instead of a positive 5. All that's going to do is flip the signs, but that makes all the difference in the world, because now I have x minus 3y and x minus 3y. These are factors, so I'm going to factor that out, x minus 3y. And then what's left if I do that? Well, the 2a and then the plus negative 5. And then, of course, we're going to clean up that plus negative 5. All right, questions? No? All right, so, oh, yes. Who was that? Yes, Emma? Okay, let's see. All right, where is the confusion rising? Okay, so I've got, so is it that factoring out the x minus 3y? Think so? Okay, so x minus 3y. This is a factor. The reason it's a factor is it is multiplied by the negative 5. Now, if you ignore the big picture, that's a binomial, right? What do you bring? The 2a in the second set of parentheses. Yes, perfect. So here's x minus 3y, here's x minus 3y, okay? Now, let's just pretend for 1 second, I'm going to let x minus 3y equal the letter b, all right? If I do that, that means I have 2ab plus negative 5 times b, right? And everybody would say, oh yeah, there's a b. Factor that out, I'm left with b. I factor out that b, and then what's left over? 2ab, divide that b away, you're left with the 2a. Negative 5 times b, factor out that b, you're left with the negative 5, right? That part makes sense? Yes, good. So now b is just a substitution for x minus 3y. X minus 3y is one number. It is one factor. I just don't know exactly the value of it because I don't know what x and y are. So even though it's got two terms, it is multiplied by 2a. So I can factor it out just like I factored this b out, even though it looks like I'm doing different math over here than I am over here, but I'm not. So what I've done is I factored out the common factor between 2ab and negative 5b, which was b. Over here, I factored out the x minus 3y from the first and the second terms because that's the common factor. And this is always going to happen. So it's important that we get this right the first time because this is how factor by grouping always works. Okay? And then when I bring that out, what is left over? Well, if I've divided out that x minus 3y, so what's left over is 2a. I've divided out that x minus 3y over here. The only thing left is the negative 5. That's okay. So I tell you what, Emma, what I want you to do is I'm going to let everybody just take a few minutes. Take a look at these next two. I'm going to be quiet for a second. I want you to work on it for a second, and then we're going to come back, and then I'll come right back, and we're going to factor some of this. Why did I make the 5x negative? Oh, so the reason I did that is if I leave this as a minus, it makes the factoring confusing. So I always change that to plus negative, that third term, and then that way I don't mess up, because when if I need to factor out a negative, it flips the sign in both terms past it. Final answer, why is it? Oh, that's just me being dumb. That is going to cause confusion. That's my mistake. Thank you for catching that. So the reason is if I don't, this is what's going to happen. I'm going to get minus 5x plus 15, factor out of 2a. That leaves me x minus 3y. And over here, I'm going to factor out a 5. So people are going to say, oh, factor out a 5, so that's left with x plus 3. And they'll say, oh, I factored out a 5, it's positive. No, it's not. It's, you factored out a 5. This was still subtract. And now if I put that subtract out here, look at what happens when I distribute back. Now I've made this negative 15. So by always pinning the sign to the third term, plus negative 5x. Now, when I go to pull out a common factor, this is negative 5x. And I have a plus, so when I pull out that 5, gosh, I am just not making any sense today. So by doing it this way, what happens? Now, if I pull out a 5, I'm left with negative x plus 3y. Instead of taking a chance of making this a minus when it's supposed to be a plus, or making it a plus when it's supposed to be a minus. If it makes sense the other way, if you can do it the other way, that by all means go for it. But this is just me trying to be consistent. And then when I need the signs to change, I just change what I factored out to a negative, whatever that was. And that gets me there. And now my two binomial factors match. So now I know I've done it right. Okay. All right, take a few minutes with that. I'm going to step out for just a second. And I'll be right back. All right. Okay, the factors outside each grouping ended up together. So did the two inside cancel out? The two factors on the inside ended up together because they're the same. So yes, then x minus 3y divides x minus 3y. Let me see if I can make one more stab at this because I think I have an idea. Trying to get too cute. All right, so and if what I say does nothing but confuse you, ignore that I said it. When I want to pull out x minus 3y, what that does is it says, okay, here's your original first term. Now divide that by whatever you just factored out. Here's your second term. Divide that by whatever you just factored out. So what happens? X minus 3y is divide, leaving a 1. X minus 3y is divide, leaving a 1. And now what's left? X minus 3y times the x minus 3y in the numerator and denominator divided away. So the only thing left is a 2a plus, and then the negative 5 is the only left there, which again gets rewritten as 2a minus 5. That either helps or makes it more confusing. I never know which it is. What do you mean by cancel out? So they divided out here, but I was only able to divide by that because I pulled it out. Right? So that means these go away, but now this one remains. And they can't be, they're not added or subtracted. So they can't be zeroed out or divided out. Okay. Let's take a look at another one, and I'm going to jump to that last one. The reason the middle one, the reason I'm staying away from that is if you try to factor it in its current form, it doesn't work. You have to rearrange. So I'm not going to mess with that right now, but I do want you to see this last one before we go, because it doesn't have a middle. In the middle there, it doesn't have a subtraction sign. So I don't have to worry about any factor, or I don't have to confuse you any. So in this one, I'm just, again, grouping the first two and the last two. I didn't change this to plus minus because this wasn't subtract to start with. And what do I have? I have x to the fifth and x cubed. They both have factors of x cubed. That's going to leave me x squared minus 9 plus, and then 8x squared and negative 72 have an 8 in common. And that's going to leave me x squared minus 9. Everybody good with that part? Okay. Yes, okay. Emma, I'm not picking on you, but does that help? Does this one make a little bit more sense, or because what's the next step here? My next step is going to be to pull out that piece they have in common. They both have an x squared minus 9 in them, right? So when I factor out x squared minus 9 from these two terms, I'm going to be left with x cubed for the first. This was factored away, so this went out to a 1. X cubed times 1 is x cubed. The plus still exists. And then I have the 8. And then this is x squared minus 9. I factored that out. So it goes to a 1. 8 times 1 is 8. Okay. Now, this one says, so pulling out the common variable. Yes, exactly. Yep. I'm pulling out x squared minus 9. That whole factor is getting pulled out. That's exactly right. I think I somehow just saw a light bulb come on from across the internet. That's great. Perfect. All right, well, now that I said something helpful, let me be a little frustrating, because these two factors, x squared minus 9 and x cubed plus 8, they're both those special forms that we talked about. X squared minus 9 is the difference of squares. So that factors into x plus 3 times x minus 3. X cubed plus 8 is a sum of cubes. So it factors into x plus 2 times x squared minus 2x plus 4. And then that's the fully factored form. If you were doing a problem like this and it says factor it all the way down, if you get from the original to this step, that's 75%. And then breaking these down again would be another 25%, I think. Because doing the factor by grouping like this is probably the toughest part. This is a perfect cube. This is a sum of cubes. This is a difference of squares. And when I say squares and perfect squares, I mean the same thing, right? Perfect squares are 1, 4, 9, 16, 25, 36. Perfect cubes are 1, 8, 16, 64. All the things where if you just run up your natural numbers, just raise it to the second power, that gives you your perfect squares. Run up your natural numbers, raise it to the third power, that gives you your perfect cubes. All right. Now, for the one in the middle, if you try to group it, sits, you're going to get frustrated. And the reason is the first two terms have nothing in common. Okay? The last two have a v in common. So if you're doing this problem, and I'm going to defy gravity here and go up, plus I factor out a t over here, that leaves me v minus, factor out a v. That leaves me t minus 42. See how I don't have a factor over here at all? I didn't break this down into two factors because there were no common factors. If this was going to work, t minus 42 would need to be a factor in both this first term of the problem and this last term of the problem. But it's not. So I can't do it that way. Whenever I'm going to factor by grouping, I need to make sure that my first and second, whatever my terms are, that they have something in common. So what I'm going to do is just flip the order and make this 7t. I'm going to carry the signs with me, plus tv minus 6v squared minus 42v. Again, there goes my stuff of making that plus and minus. Factor out what I have in common. That's a t. So that's 7 plus v. plus. So here, and this is the other time that I do this. I have negative 6v squared minus 42v. These are both negative. So I'm going to factor out a negative 6v. And if I did it right, what should be left? Negative 6v leaves me a v here. Negative 6v out of that leaves me a 7. And these match. So now I have 7 plus v times t minus 6v. All right. So sometimes you got to swap the order. It makes it easier. That doesn't happen all the time, but it does happen sometimes. All right. So, quick question: will this? Yes, it will. If you're when you get into Blackboard, if you go to collab positive number, so that means I'm either multiplying two positive numbers or two negative numbers. And then they need to add to -8, the coefficient of b. Well, if I'm multiplying to a positive 12 and adding to -8, that tells me my signs must be what? Plus plus, plus minus, or minus minus. Multiplying to a positive, adding to a negative. Okay. Everybody follow that idea. If I multiply to a positive and add to a negative, I know that I can only do this if I have two pluses or two positives or two negatives. If I've got two negatives and I add them together, I get a negative. If I have two positives and add them together, I get a positive. So this must be minus minus. Now, back to the left. So to get these last factors, or to get these last terms, I need two numbers that multiply to 12 and add to -8. What are they? Well, how many ways are there to multiply to 12? 12 can be written as 1 times 12. I know they have to be negative. If I add those, do I get -8? Nope, I get -13. What about -2 and -6? Add those together, get -8. There it is. So x minus 2, x minus 6. And that's all there is to it. All right. So we do have there is, in this case, I do have a bit of material where I expect you to have some background knowledge, right? So when I'm writing these out, this should be review. If it's not, there's plenty of practice out there, but that procedure should seem or sound familiar. So let's come over here to the next problem. I got 10x cubed plus 105x squared y minus 55xy squared. All right, so first step, are there any common factors? Yes, there are. All right, so 10, 105, and 55 are all numbers, obviously. They're all numbers. If just the first two have, well, no, all three of them end in 0 or 5, so there's a 5 in there. Right? So that means I can factor out a 5. How about the variables? Are there any variables that exist in all three terms? X cubed, x squared y, and xy squared. Y doesn't appear in all of them, but x does. All right? And when I factor out that 5x, remember what I'm doing is I'm saying each one of these terms has a factor of 5x in it. So what's left is I'm going to take my term, divide it by what I pulled out. 10x cubed divided by 5x. 10 divided by 5 is 2. X cubed divided by x is x squared. Plus 105 divided by 5 is, we'll move my notes as well. 105 divided by 5 is 21. X squared y divided by x is xy. And negative 55 xy squared divided by 5x. Negative 55 divided by 5 is negative 11. Xy squared divided by x just leaves me y squared. All right. And Now, if you have done this stuff before, if you've done factoring before, this one may be this one's definitely a little more difficult than my problem over here to the left is, because notice in that first problem, I have a leading coefficient of 1. Here I don't. My leading coefficient is a 2, so this is going to take a little bit more work. All right. So let's use the same idea that we did before. Now, my leading coefficient is a 2. That is a prime number, and that's always a good thing. My leading coefficient is prime. There's only one way to multiply to get it, and that is 2x and x, right? And again, we're ignoring fractions because, yes, you could do 4 and 1/2, but we're just dealing with integers as coefficients. So is everybody cool? X times x is 2x squared, and there's no other way to do that. So hands up if that's good. All right. That's what I like to hear. Okay. Good, good, good. So how about the last two? Well, in my last term, it's negative 11. Okay, so I need to multiply two things to get negative 11. So I have to have what kind of signs? Well, they have to be alternating, right? If I'm going to multiply two things to get a negative, one has to be positive, one has to be negative, right? So, well, 11's prime. Well, that's great, because the only way to get 11 is 1 and 11. So what do I have? Well, I've got, in some way, 1 and 11. Now, here's the part that's probably a little off, is the last term has a variable in it. We're typically used to the type of factoring we see over here to the left, where the trinomial only has a single variable. Well, this one has two, and that's fine. Because how do I get y squared? Y times y. So I know that this is 11y and y, and I've just got to figure out which arrangement do I have. Did I get it? So what are all the possible arrangements? Well, I know I'm multiplying to a negative, so I could either do, I could have plus minus, I could be looking at minus plus, and because my leading coefficient's not 1, I have to respect that I could have the y and the 11y in the wrong place. Plus 11y or plus y minus 11y. So which one of these gives me what I started with? Which one of these products, if I multiply, let's get rid of this for a second. And I'm going to nail it down to these. The second one? So the second one, if I FOIL this out, I get 2x squared. Where's my pen? There it is. 2x squared, first outer, plus 2xy minus 11xy minus 11y squared. Okay, 2xy minus 11xy is going to give me negative 9xy. So that one's not going to work because I need to add to 21. So anyone else? Oh, I think I was looking at the third. All right, let's try the third one. So we know this doesn't work, and that's information, right? That's good for us to know. So ignore that one. Let's go to the third one. 2x times x, 2x squared. Outer 2x times 11y is positive 22xy. Inner negative y times x is minus xy, and then negative y times positive 11y is negative 11y squared. Combine the middle two, that's 22xy minus xy, which is going to give me 21xy minus 11y squared. There it is. That's what we started with, right? So since that's what we started with, I have my factorization. And so what does this look like in the end? It looks like 5x times this one, 2x minus y times x plus 11y. Now, that is one way to handle that. That is not the only way to handle that. Okay, so I'm just flipping through the chat here. Another way to handle that is called the bottoms up method, whenever that leading coefficient is not 1. So I'm going to come down here and show you the process one time. If you followed what we did there and that makes sense, great. If not, that's okay. Nothing's wrong. We just need to take a little bit of a refresher or just a reminder. So the problem that I had was after I factored, I had 2x squared plus 21xy minus 11y squared. Now, the bottoms up method, which is kind of a mixture of the AC method, what it does is it lets me pretend for a second. So bottoms up says take A and C and multiply them. So A is 2 and C is negative 11. I'm going to take A and C, I'm going to multiply them, and I'm going to write that product as my coefficient. So notice the 2 goes out from in front here. And now I have x squared. The middle term is not affected. And 2 times negative 11 is negative 22y squared. Now, if this is factorable, if you can break this trinomial up, this resulting trinomial will factor. Does it? Yes, it does. Two numbers that multiply to negative 22 and add to positive 21, well, they are what? Positive 22. That's a y there. And negative 1y. Okay. Now here's the catch. Remember that we multiplied A and C together. So now I have to undo that step. And what that leads me to is whatever I found to be the two multiplying factors, I now divide them by whatever A was to start with. So there's A, and here it comes back. So some of these will simplify, some of them won't. X plus 22y divided by 2. 22 divided by 2 is 11. Y is still there. Now this one will not simplify because there's no coefficient, or the coefficient is 1, so there's no division to be done here. Whenever that happens, we can rewrite that denominator as the coefficient in front of x. And there is the factored pair. Does that match up with our factoring? Yep. That is that. Okay. Now, that is not a required way. I know that there's something called the cross method or the X method that was being taught before I came through school. If you can factor these in your own way and get the correct answer consistently, use the way that works for you. If you are not good at it yet, give these two a try, right? They would call this process a reverse FOIL. And you can imagine, so in this example, my leading A, the coefficient here of A is prime, and the coefficient for C is, or coefficient for the last term, which is C, is prime. If they're not prime, there are so many different cases that could happen. If this was 22 or this was 4, I couldn't narrow it down to just 2 and 1 every time. It could be 2 and 2 or 4 and 1, and the signs could be different. So reverse FOIL is great if I've got prime numbers, not so great if my A and C are not prime. All right. So like I said, I'm going to leave the skill practice for a video later. Questions there? Any problems following along, at least with the reverse FOIL, with not as much the reverse FOIL as the bottoms up? Is everybody okay with that? Yeah, practice. That is absolutely just like